the periodic table. Every chemistry student's best friend, or worst nightmare? Hello, fellow cosmic explorers. Today, we're diving into the fascinating world of chemical elements. You see this colorful chart in front of you. It's like the ultimate cheat sheet for the universe. From the carbon in your ex's burnt love letters to the gold in your grandma's dentures, these little guys make up every single object in existence. Now, chemistry students, I know what you're thinking. Why do we need so many elements? Couldn't we have just stuck with like 5? Well, my friends, that's a great question. And trust me, the answer is out of this world. But before we begin, if you're new here, don't forget to show your support by hitting the subscribe button and the bell next to it for notifications, and give a thumbs up as well. Let's go! Imagine a cosmic dance party in the early universe where particles like they had too much coffee. It's chaos, it's crowded, and it's hotter than a sauna on the sun. In this frenzy of activity, protons and neutrons are colliding faster than a cosmic game of bumper cars. But in the middle of the chaos, something amazing happens: nuclear fusion. Picture protons and neutrons coming together like long-lost friends finally reunited. They fuse to form new elements: hydrogen, helium, and a bit of lithium. And here's the thing. This wild mixing only lasts for a very short time, just minutes after the Big Bang. But in that quick moment, the universe makes the perfect mix for the lightest elements, getting things ready for what comes next. But why did this nuclear fusion frenzy stop? Well, as the universe kept getting bigger and cooler, the temperatures went down a lot, and there wasn't as much energy around. Because of this change, the nuclear fusion reactions couldn't happen as quickly as before. And so, Big Bang nucleosynthesis becomes the cosmic blueprint, the cosmic chemistry set that kickstarts the universe's journey from chaos to cosmos. It's a story of creation, of transformation, and of the universe itself, making something out of nothing in the blink of an eye. After the Big Bang, stars appeared and became like makers of elements, doing it by fusing atoms together in their hot cores. But just like everything in the universe, stars have a life cycle, a journey from birth to death, with different things happening along the way. In the early stages of their lives, stars are super powerful, fueled by the fusion of hydrogen into helium in their cores. This process releases energy, keeping the star shining bright for millions or even billions of years. But eventually, the hydrogen fuel in a star's core runs out, like a campfire running out of marshmallows. What happens next depends on the mass of the star. Smaller stars like our Sun switch gears and start fusing helium, creating heavier elements like carbon and oxygen. They puff up into red giants before shedding their outer layers, leaving behind a dense core known as a white dwarf. But bigger stars have a different fate. When they run out of hydrogen, they keep on fusing heavier elements like helium, carbon, and oxygen. This goes on until the core reaches iron, and here is the cosmic joke. Unlike before, fusing iron doesn't give out energy, it needs energy instead. This means the star can't generate energy from fusion anymore. That's like trying to make gold out of pennies. At this point, what happens next depends on how massive the star is. Some explode in a big supernova, throwing their outer parts into space and leaving behind a neutron star or black hole. Others quietly collapse into a neutron star or black hole without a big explosion. So, while small stars like our Sun can keep fusing helium after they run out of hydrogen, bigger stars can do something even more amazing. They can make iron in their cores, marking the end of their fusion journey. When a massive star reaches the end of its life, it doesn't just fade away, it goes out with a bang called a supernova. But the fun doesn't stop there. In the cosmic chaos of this explosion, elements heavier than iron are made. We're talking gold, lead, and up to uranium. So, how does this happen? Well, it's all about neutron capture, 2 flavors to choose from. First, there's the rapid neutron capture, or R process. Picture this. In the chaotic core of a supernova explosion, neutrons are flying around and crashing into atoms left and right. causing a frenzy where atoms eagerly grab neutrons faster than you can say supernova. It's like a cosmic game of musical chairs, but with neutrons and atoms instead of people. But wait, there's more. Enter the slow neutron capture, or S process. This one's like a leisurely stroll through the outer layers of a dying star. Neutrons drift in and out, casually bumping into atomic nuclei like old friends catching up over cosmic coffee. With each collision, nuclei gently catch a neutron, gradually building up to heavier elements over time. It's like building a cosmic sandwich, one layer at a time, until you have something amazing, perfect for the stars. Together, these neutron capture processes are process and as process work their magic during supernova explosions, crafting elements heavier than iron and sprinkling the cosmos with treasures like gold, silver, and uranium. It's like a cosmic kitchen whipping up the universe's fanciest dishes, one neutron at a time. But hey, why do atoms only grab onto neutrons and not protons? Well, it's all about that positive charge. Protons, with their positive vibes, just can't cozy up to other positively charged protons in atomic nuclei. Neutrons, on the other hand, are the ultimate cosmic wingmen. They slide right in without any trouble. Protons also help make elements during supernovas, but not as much as neutrons do. Both protons and neutrons play a part in creating heavier elements by grabbing onto them. Neutrons are often highlighted because they can grab elements quickly, making lots of heavy elements fast. So, while protons may feel a little left out of the stellar party, neutrons are the life of the cosmic bash, creating a galaxy filled with glittering treasures and cosmic wonders. Imagine cosmic rays as supercharged space travelers speeding through the universe with boundless energy. They come from all sorts of places, exploding stars, distant galaxies, and even our own sun. But how do they become these cosmic speedsters? Well, when something big goes boom in space, like a star exploding or a massive object having a cosmic tantrum, it shoots out a bunch of super fast particles into the universe. These particles zip around for ages until they finally reach us here on Earth. And get this, cosmic rays aren't just one type of particle. They're a whole mix of goodies like protons, electrons, and atomic nuclei. It's like a cosmic party with a buffet of particles. When these cosmic speedsters crash into atoms in space, it's like a crazy carnival ride. Boom! The impact is so intense that it breaks the atoms into smaller pieces. We call this the cosmic demolition derby spallation in action. Now, here's where things get interesting. When atoms break apart through spallation, they release smaller particles that can go on to form new elements. It's like breaking apart a big Lego block and using the pieces to build something new. And get this, certain elements like lithium, beryllium, and boron are actually created in space through this spallation process. It's like the universe's own DIY crafting corner. So, while cosmic rays may be the adrenaline junkies of the universe, they're also cosmic artists, splashing the cosmos with new elements in their wild journey through space. We previously talked about how supernova nucleosynthesis is like a cosmic kitchen, cooking up new elements up to uranium. But did you know that scientists have gone beyond what supernova can make and created even more elements in the lab? Enter artificial elements. These are elements that don't exist naturally, but are whipped up by scientists in their labs. It's like adding extra spice to the cosmic recipe book. So, how do scientists pull off this cosmic culinary feat? Well, they use specialized machines called particle accelerators. These machines rev up tiny particles to super high speeds, and then scientists aim them at heavy atoms like uranium. When these speedy particles slam into the heavy atoms, they can actually change their structure, creating brand new elements. It's like adding a new chapter to the cosmic cookbook. Some examples of artificial elements include technetium and promethium. These elements don't hang out naturally in the universe, they're born in the lab. And get this, scientists are always pushing the boundaries, trying to create even more new elements. It's like an intergalactic cooking show, with scientists as the cosmic chefs, whipping up new elements for the universe to savor. In summary, from the Big Bang to our labs on Earth, The story of chemical elements is a cosmic tale of creation and discovery. Stars forge elements through nuclear fusion, supernova explode to scatter them, and scientists create new ones in labs. Throughout this journey, we've seen how interconnected cosmic processes shape the universe and our understanding of its origins. Nuclear fusion is the cosmic engine driving this evolution, from the birth of stars to the synthesis of artificial elements. As we marvel at the wonders of the cosmos, let's remember that each element tells a story of cosmic creation and human exploration. It's a journey of discovery that continues to unfold, revealing the secrets of the universe one element at a time. If you enjoyed this journey through the cosmos, don't forget to like the video and subscribe to our channel for more fascinating insights into the wonders of the universe. Join us as we embark on further adventures of discovery and exploration. Thanks for watching.